All right, everyone, welcome to EE360. Friday, September 3rd of our review session. So, as you can see, we have our happy chat right here and our happy participants. Hello, welcome. And we are taking questions. So, anyone have a question for me to ask? All right, no questions. I want to talk about the 360. I think someone mentioned something, right? No. I sure am happy. Okay. No questions. Well, I have a question for y'all. Have you guys looked at the quiz that I posted on my little CMOS EDU page? No? So I made another quiz. This is an attempt and grade yourself. Obviously, it's just for attendance purposes to make sure you guys are catching up with the class. So what I did for you guys is, if you were to already attempt the quiz or print it out or do whatever you want with it. So the first thing I put on here was to define in written English what is a discrete power signal. So why did I put that? Well, because hint, it might be on the exam. And let me just increase the volume on my microphone. Test. There we go. That's better. So let me pull out my handy dandy notes. So if you wanted to know what a discrete power signal is, and I recommend everyone do this on your own notes, is on the back of these packets you can see as examples and code and theorems. But what I'm gonna get to you right now is definition. So from 1 to 31, there's 31 words that everyone here has to memorize. You don't have to memorize them all at the same time, but let's go to a discrete power signal, which is on page 67. And why did I choose this? Because this is a great introduction to what I'm about to get to. There we go. Aha, found it. Discrete power signals. So if I were to tell you to write something on the quiz, let's maximize this right here. Focus. There we go. If I were to give you a discrete power signal, and if you were to type this in written English, it's basically it's defined as P of X, which is equal to the limit as n goes to infinity, big N, of 1 divided by 2n plus 1, and we're doing a sigma summation symbol from n is equal to minus n to n of xn squared. So if you were to put this on your exam, then I think I got 2 points. Actually, one thing I gotta get to everyone is this. So you see how I put absolute values into our little x of n squared? So back when I did this exam, so suppose you had a signal x of n, and it goes something like, it goes down like this and then goes up like that and goes something like that. Well, you know that if you were to look at the entire power, if you were to add all this right here plus this, if you don't absolute value it, it's actually all going to cancel out, which means you have no power, which is not a good thing. So as engineers, to overcome that, we just take an absolute value, abs, so that we can get all this power. So that's what I'm trying to get to you. So on your exam, do not forget these absolute values. And the full definition is the signal x of n is said to be a power signal if is power if it is bounded from 0 to p of x to infinity. So that right there is your full definition. So right there, 3 points, I think. I don't know. So that is probably one of the definitions he might throw at you. Could be an energy signal. It could be the analog version. The point is, this is a power signal. So that's one of the words I'm trying to get to y'all. And I'm about to get to another example too. So let me show you the other thing we had on that little quizzy that I wrote. There we go. So if you were to give you this definition on the exam, a discrete power signal, how would you write it? The way I have it right there. P of x, limit n is equal to, as n approaches infinity, 2, and then 1 divided by 2n plus 1. Why the plus 1? Well, let me show you. So if you were to have a discrete signal, someone's probably asking this, x of n, and it's got 1 point there, 1 point there, 1 point there, it's 1 point there, and 1 point there. If you were to count all the points in this signal, how many points do you have? Use a blue marker. You have 1, 2, 3, 4, 5. Well, you can count 1, 2 here. We have 2 negative points, 2 positive points, and then you have this middle point. It's this middle point that we're counting when we have this 2n plus 1 condition. So for analog, well, you don't really need to worry about that middle point because it's all analog. But for discrete, we have this point at n is equal to 0. That's the reason why we got this plus 1 that happens. So if you forget this plus 1 on the exam, Dr. Stevie will take off a point. He'll probably just, like, if he were to grade it, like, oh, he'll just circle that and be like, you forgot it. So don't forget it, and then don't forget this. Don't forget your absolutes. If you forget that, you'll be sad. So now the next thing I want to lead everyone into is with the following. So the other thing I put on your little quizzy is how to evaluate something. So this is something he might also throw at you. So let me get to that one. Actually, should I go over this one? Actually, let me go more in depth into what a power signal is before I talk about the quiz. All right, so let's talk about analog signals. Analog. So everyone knows what an analog signal is, right? It's basically a continuous time and then continuous amplitude, which means it's basically a signal where it's, okay, if we had a variable t, it covers every number, and it just covers infinitesimal. It's continuous amplitude, continuous time. It all flows. It's all nice, wiggly, and we're all happy. Let me check if we have our chat. Our chat's pretty okay. All right, there we go. So I'm about to talk about analog energy, analog power, and then a case where you don't have an energy or a power signal. So I don't know how Dr. Stever's been helping you or explaining it to you guys, but I'm going to try and put it down to an engineering student level. So the best way I can explain it to you guys is, what if I give you the following signal? Let's give you this signal. X of n, or x of t, sorry. And x of t is basically, well, this little hump. I'm just going to do this little hump like that, and that's it. Begins right there, ends there. So the first thing you should look at, well, is first, actually, let me explain myself. You're going to look at an entire signal, the signal that's given to you. And you're going to go from the beginning of time. So t is equal to minus infinity. You're going to look at wherever your beginning of time signal is, so wherever it starts, to the end of time. Okay, you're going to look at the entire signal. And then after that, you're just going to absolute value it. You're just going to add everything, and you're going to absolute value it. So in English, the energy of a signal is basically the limit as big T goes to infinity from T is equal to, let me remember the full definition. Let's see, don't want to screw this up. Analog power, analog energy. There we go. Oh yeah, I was right. T, so negative T, there we go, of x of n squared. And then I think this right here has got to be a d, dt. There we go. So this right here is basically the full definition of what is an energy signal. And let me just verify that I've done that correctly. Find that as, and let me just pull this out so that you guys know what I'm talking about. Page 61. And yeah, that's the full definition. And how do you tell if it's an energy signal? It's only an energy signal if it's bounded. So aka it's finite. You can add it. It doesn't go into infinity. So if I were to add this signal, and you see how if this particular signal, if we were to add it from minus infinity to positive infinity, absolute value, and then square it if you want to get us power if you want, it's finite. Which means this signal here is actually an energy signal. Okay? Makes sense, huh? Now, I'm gonna transition this into what is a power signal. So I almost said the P word. That's a keyword for another lecture that I have later on. Actually, right here, let me just talk about it. What is a power signal? So let me explain it to you. So remember how back in 220 you were given the following signal. It's just periodic, right? And what's his name? You were told that simple equation. I think it was root mean squared. No, I don't think so. That's it. Where you take the integral from, let's do pi over 2 to pi over 2 of whatever your signal sine of t or something like that, dt, right? Oh yeah, and then you absolute value that. So point is, what I'm trying to get to you is if you add this entire signal and you would try to get the average power, what's the average power of sine? It's always going to be 1/2 the average power of sine Remember that? Remember that in 221, 220? So the full definition of a power signal, and this is what Dr. Steve was trying to get to you, and I'm going to try and explain it first, is suppose you had this periodic signal that kept doing this forever. It kept doing this forever. So x of t. and it keeps doing this periodicity from the beginning of time, t is equal to minus infinity, to the end of time. As you can see, if you were to add this entire signal and the absolute power, so the absolute value of it, you're going to see that this number keeps getting bigger, which is bad. So one thing as an engineer we try to do, and let me see if I can get a, should we use the purple? Yeah, let's use the purple. Is the other variable we have to play with is time. So as you notice, if we were to just add this section right here, we can take the absolute value of this and then divide it by the time, so t1, right? However, if we want to keep going, like, okay, instead of adding this, we're going to add this. So as we keep going to infinity, how do we keep this signal from not going into infinity? We just divide it by a bigger time, t2. All right? Now you see the pattern, right? As engineers, you see the little OCPD pattern. Let me pull out another. I thought I had a green marker. Yeah. Oh yeah, let's pull out the green marker. So what I'm trying to get to, everyone, is we have a periodic signal. How do we keep it bounded? We just add it by however much time you have. So from here to here, t big. All right. So that's how you integrate an entire power signal, an entire periodic signal, and then keep it bounded. So this is a keyword I'm trying to get to. Okay, this is page 2. The full definition of a power signal, an analog power is basically defined as p of x, which is equal to the limit as t goes to infinity of time is equal to t over 2 minus t over 2 of the entire signal squared dt. All right, and we divide it all by time, depending on how long our time is. Actually, I think this should be, yes, just that time. So let me see if I got that right. There we go. You want your hard definition? There you go. T 1 over t. So the only difference between the energy definition and the power definition. Here's your energy definition. Actually, let me write that down. Analog energy. The only difference is this 1 over t. So that's how we keep stuff bounded. So if you were to put these two together, here's energy, and then here's power. Oh, but then you see these bounds are different. How do you get them to be the same? Let me write that down for you. All you got to do is just change this bounds of integration. So just make this wider, but then you got to divide it by 2, which is limit of 1 over 2t from t is equal to minus t, time is equal to positive t of x of t squared dt. And then this right here, I'm just going to circle that squiggly, is basically the definition of energy. So if you were to write this, limit as t goes to infinity, 1 over 2t, and let me just write this in green, E. And now you can see that connection. So what I'm trying to tell everyone is if you were to analyze this picture right here, if you see something finite like this, and you add the entire signal in absolute and square it, and if it's finite, then it's an energy signal. However, if you're given the case where you have a periodic signal, and here's the word, and I'm going to tell you this word, but periodic. So when you hear periodic, automatically assume it's power. As you can see, it doesn't end. The only way to make it finite is to divide it by however much time you add. So that is your difference between power and energy signal. And now let me tell you a really simple signal. So what if it's not a power or an energy signal? Here's a great example. You guys are gonna like this one. X of t. There you go. Like that? This is the problem. I think it's in exercise 5. It's the exercise 4, the last problem. It's the absolute value. And now let's just look at it. If we were to go to like the beginning of time is equal to minus infinity. So if you were to add all this, as you can see, it's a lot of adding. And if you go to the beginning of time, that's also a lot of adding. So as you can see, it's not an energy signal. So if we try to add it, it goes to infinity. However, if we try to divide it by time, even though our time is getting bigger, this signal also gets bigger. It's not periodic. The key word is periodic. That's the word. If you were to get out of this class with one thing, remember, periodic signals are power signals. Tell that to Dr. Stewart. He'll be surprised. So in this case, the absolute, if you were to give this signal t, this function right here is neither a power or an energy signal. So what I'm trying to get to everyone is let's stop thinking theory. Let's stop thinking, oh, math and stuff. Let's start thinking practical engineering. What do we have? Oh, we have a signal that is not periodic and it just gets big if you were to add it in an integral. It's not a power or an energy signal. Or, oh, I'm given this blip or this piece of information. Oh, it's an energy signal. Or, oh, I'm given a periodic signal. It's a power signal. So keywords are, if it's finite like this, energy. If it's periodic, power. And if it just goes to infinity like this, it's neither. All right? Does that clear stuff up? And then this, you can also apply this to the discrete version, but I think it's easier to explain it in the analog case. So that's what I wanted to get to, everyone. That's the reason why I made this quiz right here. So that's why I was trying to talk to you with a discrete power signal, but this is easier, right? But that's what I was trying to lead everyone. Is everyone happy with that? Is that a good review? Because I'm about to go over number 2. No. All right. Let me check if I'm still recording. Yes, I am. All right. Now the next thing I'm going to talk about, and it's the properties of the Dirac delta. So the reason why I picked this problem right here is for the following. I want to make sure you guys know how to even do this. Okay, there we go. Let me write that down. Evaluate. If I were to give you this integral from t is equal to infinity, t is equal to minus infinity, t cosine pi of t, d Dirac of t minus 1 divided by dt. There we go. So if I were to give you this problem, or not me, Dr. Stubert, were to give you this problem, do you know how to solve this? So remember that one theorem And it was that one theorem you guys saw on Wednesday. And if you were to be smart like me, you would go to the back, and you know this is the derivative sifting property, which is located on page 80. That's a weird typo. Okay. There we go. Actually, he's got a good problem right there. As you can see, if you were given this derivative or d of a Dirac, you get this -1 depending on the n, however many derivatives you have, and then you just take a derivative of the function itself. So I want to make sure everyone can do this. The reason why I gave this quiz is that if you can do this and you can do this, then I know you're going to get some points on this exam. And plus, if you listen to the explanation of how to get this analog power signal, then you'll definitely do great on the exam. So let's do this problem. So the first things first is, because we have this Dirac delta, what we gotta do is, first we gotta put this -1, put that negative right there. Just put it right there. Okay, don't forget it. Then we take a derivative with respect to time of, let me just underscore it or underline it, of this function. And I'll just write it like this: cosine pi t. And then, because I have OCPD, when does this turn to 1? When t is equal to 1. Okay, write that down. Okay, so now you have your problem that you can solve. So if you were to remember the product rule, let's do this. Let's put our -1 right there. Don't forget that. Times. And because we got to go slow, we're going to do t, and then we're going to take a derivative of this, which is basically minus sine of pi of t. However, remember the chain rule, times pi. There you go. And let's do plus. And then let's do cosine pi of t. And then the derivative of t is just 1. There we go. However, remember what I just said? Let's put that there. We have this t is equal to 1 condition. So all you got to do is just put this everywhere you see a t. So if we were to rewrite it again, we're going to put a 1 right there. And then this becomes -1 sine of pi times pi plus cosine of pi. There we go. And then start rewriting stuff. Let's put that -1 right there. And then what's sine of pi? Sine of pi is 0. So this thing just dies. Plus cosine of pi. And what's cosine of pi? -1. And then you got this -1 and this -1. And what are you left with? 1. That's why I chose that problem. Or that's why I made this little problem, because it's 1. So do you see how I did that problem right there? So the key things I'm trying to get to you is, if you were given this little d of Dirac of whatever this thing is, don't forget this -1. Take a derivative of this and then evaluate it at t is equal to whatever makes this one a non-zero, or makes this 1, which is at t is equal to 1. So does that make any good sense? Is this clicking onto anyone better? Is this helpful? Chat, how we doing? Make sense? Is this really helpful? No. Ah, it's okay. I'm just kidding. Ah, definitely. So the reason why I'm trying to do this, the reason why I'm doing these little quizzes, is to make sure you guys are confident that you guys will do great on the exam. So everything I talked about today and in this session should be really good. Especially review that power. Actually, let me go over one more thing. Maybe one more thing. So this is page 4. If I were to give you, okay, Aldo, can you explain where you got the -1? My audio, it's from the sifting property. It's that weird derivative sifting property. So if you were to go to theorem 1.14, this is a theorem. So if the nth derivative of f of t exists, and he gives you this, so actually, let me just zoom in. You see that right there, that d of n with respect to Dirac of that? You see that? That's where he gets that -1. But depending on the power, the derivative, so the first derivative, you get -1 to the first, which is just -1. If he gives you a 2d2, then instead of this being minus, it's actually a positive. But I don't think he's going to trick you like that. I think he's just wanting you to know that if you see this, then just put a minus. But now you know where it comes from. All right? Makes sense? Yes. All right, perfect. Okay, thanks. Hopefully, let me see if it's recording the chat. Yes, it's recording chat. Perfect. All right, so I'm about to give you some bonus content. All right, so what signal could he give you as an energy, power, or neither signal? So as an engineer, we want to have a basic case. X of t. So all signals have some type of amplitude, okay? Amplitude A, all right? However, and you'll learn this later when we get to the Laplace transform. Oh, that's the word for today, Laplace, yeah. I'm just kidding. We're gonna have some type of exponential. So let's just put an exponential e to the a of t. So as time goes by, you'll have something. The signal will either grow or decay depending on what this alpha term is. And now, does it spin? Does it do any cool wiggles? E to the j omega t. So this right here is the most basic signal of all time. If you were to memorize one signal for your entire life, is that every signal composed in signals and systems has an amplitude. Let me write that down. Amp. All signals either increase or decrease, or increase okay, this. And then all signals, and let me just write it with blue, either will have some type of frequency. Okay, so if he were to give you this, and I think he might give you this on the exam, he might say, all right, David, or all right, students, how do you make this a power signal? And remember what I just said to everyone in the beginning of the class? How to make this a power signal? So first off, or actually, let's talk about energy. Remember energy? We have an energy signal that just, it's just simple, right? It just stops. So how do you make it stop? So first, you gotta have no period, so this W term has to, for some reason, go away. But this alpha term, you have to have it decay. So as time goes to infinity, alpha has to be less than 0. And then time can be bounded like this. So point is, if he were to give you this, you can say, okay, alpha needs to be negative. So if alpha were a e to the minus t or something like that, that's the simplest one. As time goes to infinity, it decreases, which means it's finite. And I think he actually might give you, I think you can actually do an absolute value. Should you do it? Because then if it goes the other way, this gets to minus infinity, but to cancel the infinity, because it might grow that way. Actually, I think this might be right too. But point is, you gotta control this. So now, how do you make this a power signal? So this is an energy. There we go. Let me move these notes. Let me check my other notes that I have right here. There we go. There we go. Actually, let me try to explain to you guys some better. So if I were to give you, so ignore this one. If alpha was a positive number, then you're going to get the following case where it just increases like that. So if this alpha were 1 or 2 or some positive number, you see it increases. And you should probably already know that. As time goes to infinity, this gets bigger. What does that mean? It's neither power or energy signal. So easy point, easy couple points. Alpha, if it's alpha's positive for this signal, it's neither. Okay, and now how do you get to the point where, oh well, I want it to be finite, I want it to be power, I wanted it to be a periodic signal. If alpha is equal to 0, so that means this term is just nothing, it's just a straight line. Which means if you want to make it wiggle, this is where this term comes to play. And now you can multiply by j omega, and now you have a periodic signal, which means now you got a power signal. So you see how this is making sense now? And then if you wanted an energy signal, so actually, let me do this. This is neither, and then this is power, which is equal to periodic. So that's our key word for today. Write a star. And now if you want energy, this alpha term has to be less than 0, so it has to be a negative number. This is negative, so I'm going to write pause, and then 0, and then this is neg. Okay, I'm going to write these words down just in case someone's like, oh, I gotta find some keywords. So if alpha were a negative number and it decays like this, then it's an energy signal. However, you got to make sure the other side goes down too. So this is where the absolute value comes into play. So I think it's something with this, so you can discover that on your own terms. So does that make any more sense? So if he were to give you this on the exam, Dr. Steve were to give you this on the exam, can you figure out how to make it a power signal? Can you figure out how to make it an energy signal? Do you understand what this term is? This is just an amplitude. So your DC term or your gain, alpha, you see it's always there. It's always in every signal. Every signal has an amplitude. And then, do you understand what this term is? This is basically your exponential. You're decaying, it's increasing. You can see this or you can see that. Makes sense, right? And what about this j omega term? When you see j omega, think of it's a circle. It just spins around. So if you can all see an imaginary signal, it would look like this. However, if you want it to be a real OCPD engineer, this is page 5. Let me get to one more little tip. And we won't learn this until later on, but I'll give you guys a hint on what I'm trying to do. If I were to have some signal a e to the j omega t, you know that this signal has a real and an imaginary component. So in our oscilloscopes, we always have this signal. Any real signal will be shown on an oscilloscope. How do you see this? You can't see, well, maybe you might see it like partial of the times. However, the only way to see this is with its complex conjugate, e to the minus j omega t. So then the imaginary components just cancel out, and then all you're able to see is the real part. So this is what you actually see in an oscilloscope. And if we were to dive even deeper, if you were to have a spectrometer, so a spectrometer or some spectrogram is a function of a frequency, and then you have your amplitude. So if you wanted to see this signal, e to the j omega t, which omega can equal to 2 pi f, right? 2 pi f naught. Is that tau on the oscilloscope? It's time, yes, time. And then here's your amplitude. There we go, right? So I'm about to show some, like, this is all optional information right now, but this is to help you see what I'm trying to show you. If you were to have this omega naught, 2 pi f naught, this is what it's going to look like on a spectrogram. It's just going to be literally this spec, which is just a function of frequency, which is the spec, f naught. However, in reality, to add a real signal, to get the real component, all real signals have a complex conjugate, minus ft. So if you add this signal, where's my green marker? Aha. If you add this signal and you get this signal, this plus this, you'll get real. You'll get what you see on an oscilloscope. So this right here is stuff you'll learn in 361, but I'm trying to show you this right now, show you this early to hopefully open your minds to why signals and systems is so important and how much more we'll have in store for this class. So is that helpful for everyone? Was this a really good study session? Man, we packed a lot in like 45 minutes. And did you guys learn a lot in this one or learn more in Dr. Stewart's? No, man, we like reading the book. Oh, you guys like reading books? Okay, just kidding. Nah. Like, the reason why I wanted to do these types of lectures is to get you guys to stop thinking theory. Like, you guys are talking too much theory. Like, oh, just read the book. No, I want to get you guys exposed to, like, oh, this stuff is actually practical. It's not just math. Like, it's stuff you can see. Like, let me go back to what I was trying to show you guys, and you guys better study this. If you don't, I'm gonna be sad. This, like, you can see an energy signal. You know what it looks like. It's not math. It's not math. It's something you can look at. Oh, look, energy. Oh, wait, a periodic signal. Oh, power. Or page 3. Here we go. Or, oh, look, a signal that just does this. Oh, it doesn't exist. It's neither power, neither energy. Makes sense, huh? Alright. See how I'm trying to get you guys going? This is the mindset I'm trying to get to you. The Baker mindset, if you want to call it. Like, oh, how do you get stuff to work? So that's the reason why I wanted to do 360 again, because this class is like really, really important, but no one like tries to like help the students. Like, it's more like every TA that ever does this class is like, no, just copy the assignment, copy this. I don't even know what's going on. No, the TA's got to know what's going on too and engage with the students. So, was this really good? Did you guys like this? Yes. No. Maybe. I like it. We love it. I see. You guys use the love word. That's really good. So, does anyone have any other questions? You guys have any concerns? Any Matlab? How's everyone doing on the Matlab, by the way? Is Matlab good? Matlab easy? You guys know how to publish, right? Let me type Matlab. if I were to pull this puppy out, chat. Let me see. Let me pull this puppy out. So you guys know how to publish. Haven't had time to start on Matlab, but been messing around with it for EE330. Yeah, I remember 330. I can show you guys something. I think one of the most important things that I want to talk to you guys about is, let me see if I can give you guys some additional help. So you guys know you can look this up, how to integral Matlab. There we go. So if you ever want any help, you got Google. And then if you wanted to look, I think he gives you this, Dr. Schill, how to do an integral. And there's like a couple ways of doing it. Let me see if there's the way I like doing it. I think this is the way right here. This is the way I like doing it. So is this the one? Or let me check how else does he do it. But yeah, this is probably one of the most important functions in EE330 because you guys got a lot of integrals. So if you were to use this. Oh yeah, and plus all these examples on Matlab, you can try this example, as in you can just copy it and paste right there. So let me see if I can dissect this for you guys. Oh yeah, by the way, if you guys want to make a comment, it's nice to comment your code just in case you were to go back in time and say, oh, I remember that Matlab assignment. And trust me guys, the assignments that I've edited for this entire 360, I put a purpose into them. So just in case you ever want to go back to your assignments, you can look at them like, okay, this first assignment, maybe you might not have practice, but the next assignments you'll see coming up, you're going to see the practical purposes behind all these assignments. So if you were to put this function, let's talk about this. So the function that we have is, well, 1 divided by this, where our play variables are this and this. Let me see. What are they trying to do with this? Evaluate the integral from x is equal to 0 to x is equal to 2 at a constant. Oh, I know what they're doing. So they're creating a function, but they're creating like a pseudo function. So let me show you what this means. So he created a function. So this function can be created. Let me just run this. Evaluate F9. So doing this, if you do this, it creates two variables, x and c. So your play variables are x and your other play variable is c. So if I were to move this right here. So you have this function, two play variables, x and c. X and c. You can do whatever you want. And now if you were to call the integral function at x, or x for integral is going to be, well, yeah, x. Now we're going to call the function. So he's literally, if you were to just copy this, maybe this might work. Actually, not keep it like that. So the play variable is x, c right here is 5, and then let me just type this right here. Help integral. There we go. And then if you were to read this, the function a to b. So these two, this right here is from the beginning, from a to b. So this is a funny way of doing integrals. And if you were to run that, there you go. And then you're like, oh, what if this c is like 0? You can make 0. There we go. Actually, let me do this. Play variable. So if you wanted to play with that, play with the c variable. Remember it was 5. Run that. See? And then, oh, let's make this c equal to 0. See that? And I guess it's giving me this integral may not exist. Oh, because when x is 0, this is 0, this is 0, that's also 0, which means that's 1 divided by 0, that's infinity. So don't put 0, maybe 0.1. And oh, that's actually also too big. Actually, no. To make it positive, 2.2 or 2.1. There we go. Oh, okay, whatever. 5, 4, 6. All right, we found some number that it just doesn't like. The point is, when you see this, it's probably because it's saying you have a singularity. Another way of saying singularity is infinity. So maybe I'll help you guys with 330. Maybe I'll do a video if you guys want. 330 is not that bad. It's pretty fun, painful, but not that bad. Maybe I'll help you guys if you guys tell me what's going on. But you see how Matlab can be really, really helpful. You have Google. You can look at these examples. It walks you through how to do it. And it's a tool. So use it as happy as you can. It doesn't solve problems for you. It just helps you calculate values, just crunch numbers really good. So don't think it's oh, EE330, I'm just gonna punch in my math homework. No, the physics is what you gotta come up, and then you come up with these equations, and then MATLAB crunches these equations for you. So don't think of it as almighty problem solver. It just helps you crunch numbers. You'll probably see that in one of the assignments for 330. But does anyone have any other questions? Okay, let's go back to this. If you were to do the assignment, if you were to turn this in, 360. Suppose you have your exercise 1A, and then exercise 1B. You see how it's organized like this. You have these double percent signs to keep stuff organized, right? See how this, and then if you want to create a section like this, and then actually let me just type in here. This is how to append signals. And then you can also do that too. Exercise 2, exercise 2A. I'll show you this. Publish. Click here. Edit publishing options. Don't do an HTML. Do a PDF. Publish. And then this is a great thing to explain. So if you get this error, when in doubt, always change folder. So basically, you see how this folder right here is not our usual homework. This is our solutions, by the way. Just kidding now. I try to make sure you guys, the solutions are basically your hand calcs. Don't worry, I'll tell you guys about that later. But point is, to change your folder, you change this directory. Watch this. See? Now we're working here. See, remember all that stuff we were doing in class? Boop, 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 boop. And this is probably what your assignments are going to be doing. And then run your time. And then you see how it's so organized. And plus you can click on it. Oh, I want to see what your ramp function looks like. Click. Look. And it gives you this. If you do the double percent signs, it organizes it like this. See how it's so organized? Then, remember that new section I did? Exercise 2, append signals. And then, let me go down here. See this? If you do this format right here, you get the following. See? This is how to append signals, and then exercise 2A. So organized. So this is what I expect from everyone, to try to do this like it's easy. If you don't do these double percent signs, you're gonna get the following, and it might look really ugly. Let me show you guys an example of what ugly looks like. Okay, let me publish that. So it's gonna do its thing again. Now this is what an ugly paper looks like. Okay, right here. Now you see? And then look, oh, you have these figures that pop up, but nothing prints out. Uh-oh, what's going on? Oh, where are my figures? And then, oops, I forgot to semicolon this. That's not good too. And then, oh, look, they all stapled at the back of the paper, which is really annoying. Unless you title these, I recommend please put the title exercise 4E or, oh, now you know what it is. Because the reason why I make you guys do titles is just in case this does happen, I can at least tell what it is. See how if you don't put those double % signs, you get that nasty mess? There we go. Control Z, Control Z, Control Z. See? There we go. So, and then what was the other thing? Okay, here's the final thing. So, when in doubt, you're probably asking, David, how do I tell if I'm not suppressing stuff? So there's this little button right here. It's on the corner of the top right. If you click here, it gives you all these errors. It tells you like, oh, warnings found. Click here to get to the first message. If you click here, it tells you, oh, terminate with the semicolon. Okay, do that. Click here. And then, oh, I forgot to put a semicolon there. And plus, you'll see the squigglies. You see? Let me click here. Let me show you. See right there? You see the squiggly right there? Gives you the error, tells you, oh, what you could do to improve it. And then look, error goes away. And then semi. And then click here, semi. There we go. And this is how you clean your code. And then let me show you the cool bonus feature at the end. Ooh, this is a problem. Here's a problem. Why is this J squiggled? It says, for improved robustness, consider using replacing I and J by one I. So it doesn't like this. It still runs, but it suggests if you want to make your code run a little faster, use one I. And then look at that. They disappear, all the errors, and then you get this nice green thing. So that when you publish, watch this, nothing gets printed here. You have a really clean code. Boom. See that? And now you can submit this to me and you can all be pretty happy. For exercise 2B, do we need to plot it? Okay, I know what you're talking about. Let me go to let me see. Where is the other page? Aha. Let me pull out the assignment. Assignment 1. Okay, 2B. Yes, and if you didn't see the other video I posted, the advanced Matlab tricks already teach you how to do that. So let me show you. Let me see if I did that here. 2B. Yes, I did it. So if you go to the other video I posted, which is titled Advanced Matlab Tricks, I talk about this. So you could have done the comment version. The value of R3 is, and then you can do this R3. This right here is not clean code. Well, it might be clean if you wanted to. Oh, R. Oh, that's because I erased it. Let me just run advanced. Run in advance. Run in advance. Run in advance. There we go. There we go. And then run section. So you could do this, and this will print out. You'll have this comment, and it'll print this out. However, this doesn't look as professional. So the professional way of doing it is, instead of doing that, you can do this. Clean. The third sample in R of n is this percent decimal. And then I put this because we're doing new lines. And then you can do this. Looks really clean, huh? And then look, then you don't get these errors, you see? It's all gone. Oh yeah, and you're probably seeing this. Just in case you get confused on like, oh, where did I put this variable b? How many times have I instantiated? You can look at where you've instantiated. Or what about this cosine? Actually, no, not cosine. Stem. How many times have you used stem? Or actually, no, that's a bad one too. X. And then you can see when you used it. See, you used it 2 times. 1, 2. And it tells you the line too. So you can see how Matlab is really helpful. And you can do a lot of things with it. It's pretty fun. So, oh yeah, how many times have I used this pretty graph function that we've all created? See this one? This is how you create it. Double click. Oh look, we've used it a pretty good amount of times. And we have no warnings. Really simple, huh? I'm gonna make sure you guys all love Matlab. You guys are gonna be like using Matlab to like publish like all your reports or your 320 labs or something like that. You can use this in anything if you wanted to. It's such a good number cruncher. Are there any other questions from the participants or anyone in the chat? Was this a really good review? Pull out the camera. Thanks. Extremely good. Oh, that's good to hear, guys. I do this for all of you guys. I want to make sure you guys are getting your education's worth. I know how it feels like to have a TA that's lazy. I don't want to be the lazy TA. I want to make sure you guys are confident and have one less thing to worry about. You guys have 330 to worry about. Well, in that case, I think we can end our day here. So I'll upload this video for those who haven't made it to this section. Please review this. I'll make an announcement when I finally get this uploaded. The notes will all be uploaded. And assignment is due Tuesday at 10 a.m. next week. Usually it was supposed to be due Monday, but because it's Labor Day, yeah, everyone get an extra day. 10 a.m. I will start grading them so that once I finish it, guys, I can get the assignment out for you guys. And then I think Wednesday I'll probably bring in the second assignment, or I'll think about it. Assignments are usually due before the exam. There's 6 big assignments, 6 exams, so I'll let you guys know. Don't worry, I'll carry you guys. So with that, any other last second thoughts before I end the video? Thanks, David. No, thank you guys for coming. How many questions? I think there's going to be 3. First one's going to be definitions. Second one's probably going to be something regarding power. I'm assuming it's going to be power. And then the third one's definitely going to be, can you do your mathematics, which is this. Can you do this? So I recommend looking at the book. Read the book. Please just read the book. Go through the examples. Memorize the definitions. He can throw whatever he can, but the 3 things are, he's going to test your definitions. So probably going to be 5. The second question is, he's going to test your power, your signals. Do you know what a signal is? Can you define a signal? What's the amplitude? If it's increasing, decreasing, is it power? Is it energy? Is it neither? And then the third one is, can you do math? What's a Dirac delta? What's a Kronecker delta? Can you do the derivative, shifting properties, anything like that? So should be a really simple exam. You guys should be fine. All right. What are the back index to see? Where are the back index? 3rd edition. Where is? Of the book? Oh, an emoji. Wow, our first emoji, guys. Well, if you look at the book, everyone has it. You can look at all the definitions you ever need to memorize right here. So there are 31 words. So everyone gets something. Like he can give you this, or he can give you this fundamental frequency of a periodic analog signal. Make sure you know how to do that. He might give you what's a Hermitian even signal. That's the 4th edition. No, this is not the Shams outline. This is the book he gives you in person. His unpublished book, which is called Deterministic and Stochastic Signals in Linear Systems by Dr. Stuber. This is his book, not the Shams book. This is his book. Oh, you haven't gotten the book? Oh gosh. Yeah, this is the biggest thing. Please keep all these notes. I use this all the time in grad school. Like undergrad, it's kind of boring, but in grad school, oh, you see this all the time. So I trust me. The notes he gives you, this is gold. It's literal gold. All this stuff right here, all this examples. I'm trying to push him to please publish this book. It's really, really good. So I'm trusting you guys. This guy's a really good teacher. He just has a hard time explaining it to a lower level, but that's my job. All right, y'all. That's a day for me. All right, I'm gonna end the video now.